We've now been talking about quantum mechanics for a little bit here, and quantum mechanics are going to allow us to mathematically calculate the energy of atomic orbitals. And we can do this by using the Schrödinger equation. And the Schrödinger equation looks very, very innocent, but it's probably one of the most complicated mathematical things to calculate in all of chemistry. And the Schrödinger equation is H psi equals E psi, where E is the energy that we can use to calculate this. And this psi term is called a wave function, which corresponds to a certain energy and describes a region about the nucleus an orbital where an electron having that energy may be found. And in this class, we are not going to worry about solving the Schrödinger equation. I'd like to use a quote from the movie Tommy Boy, where Tommy uses this quote that says, "I can get a good look at a T-bone steak by sticking my head up a bull's ass, but some of the times you gotta take the butcher's word for it." In this case, just take the butcher's word for it. I'll be the butcher. I'll tell you that we can calculate energy using this equation. But unless you know differential calculus, you're not going to be able to solve this in an easy way. So what this Schrödinger equation allows us to calculate, or we can now look at representations of these orbitals. The different types of orbitals are the s, the p, the d, and the f. There's one type of an s orbital, 3 types of a p, 5 types of a d, and 7 types of the f. We're going to be looking at the s, the p, and the d in this class. So an s orbital, there's one type, and they can be represented by a sphere. And typically, that sphere is shaded in just like this. If we have a p orbital, there are 3 types of p orbitals. There's the px, the py, and the pz, and that's how they are represented in 3-dimensional space. So if we have the z-axis pointing straight up and down, the p orbitals are these figure 8 dumbbell type shapes where we have the pz. If this is the y-axis right here, we have the py, and then the x-axis, or the px orbital, looks like this. All 3 of these are the exact same shape and the exact same size. They're just rotated 90 degrees in 3 dimensions. There are 5 different types of d orbitals, and these get a little more complex in terms of drawing them. The first is the dz squared, which is right along the z-axis. Part of this orbital looks exactly like a pz orbital, except there's a donut around it. And we shade in either the donut or the two lobes in this orbital. Then there's the dx squared minus y squared, which falls right along the x and the y axis. And it looks something like this, where you have these figure 8 orbital lobes, and every other one is shaded in. So there's your dx squared minus y squared. The dxz is the next orbital, and that orbital falls directly along the xz axis. So there's going to be a lobe in each of the 4 quadrants of the xz plane. If we look at the dyz, it's going to have a lobe in each of the 4 quadrants of the yz plane. Then finally, we have the xy orbital, which is going to fall directly along each of the quadrants in the yz plane. So each of these orbitals, the dxy, xz, and yz, are exactly the same shape, except they're also rotated 90 degrees in 3-dimensional space. When we go on to further chapters, we're going to talk about how these orbitals interact. If you don't know the shapes of these orbitals like the back of your hand, and if you can't visualize them in 3 dimensions, you're never going to be able to visualize how these orbitals will interact with each other. So it's very, very important and very, very vital that you know the shapes of all of these orbitals. In the next video, we'll discuss what the energies are of each of these orbitals and how we can fill electrons into those particular orbitals.